This is Lesson 24 in our Calculus 1 series, Area Under a Curve. In this lesson, we learn how to find the area under the graph of y equals f of x over the interval ab. So we're talking about this shaded area here. And just for simplicity, we're going to talk about functions f of x that are greater than or equal to 0 on ab. And we're going to approximate the area under the curve by dividing the interval ab into n subintervals, and using a rectangle to approximate the area on each subinterval. And then to get the exact area, we'll take a limit as the number of rectangles approaches infinity. So let's take a look at what that looks like. Here we have our interval AB divided into, in this case, 4 subintervals. N is equal to 4 here. Delta x is the width of the subinterval, and so we're going to take equally sized subintervals, so delta x is equal to b minus a divided by n. And then we're going to approximate the area on each subinterval by using rectangles. So this is one example of how we can set up rectangles, of which we'll take the area so that we can approximate the area under the curve. Let's talk about a few specific ways to set up those rectangles. A left-hand sum says that for the height of the rectangle, we use the function value on the left of the subinterval. So that says for the first subinterval, x0 to x1, we look to the left side of that subinterval, that's at x0, and we take the function evaluation there. So we're using f of x0 to be the height of our first rectangle. Then on the second subinterval, again, we look at the endpoint on the left of the subinterval, that's x1 in this case, and we take the function evaluation at x1, and we use that as the height of the rectangle. And so on for the other subintervals. This is a left-hand sum. And so for this picture, the area under the curve is approximated by f of x0 times delta x. We've got the height of our first rectangle multiplied by the width of the rectangle, plus f of x1 delta x. Now we're on the second subinterval. We've got the height of that rectangle multiplied again by delta x, plus f of x2 delta x, plus f of x3 delta x. And so we could write that using sigma notation, either with I starting at 0, I going from 0 to 3, f of xi delta x, or I going from 1 to 4, f of xi minus 1 delta x. And we typically like to start I at 1 and talk about the ith subinterval. So this is the first subinterval, and we have 4 subintervals. So typically we'll use I starting at 1. And then in general, the left-hand sum looks like this, the summation I going from 1 to n, f of xi minus 1 delta x. Similarly, we could talk about a right-hand sum, where the height of the rectangle is given by the function value on the right of the subinterval. So now for the first subinterval, we're using f of x1, because x1 is the value on the right of the first subinterval. And then for the second subinterval, we're using f of x2 for the height of that rectangle. Then for the third, f of x3, and for the fourth subinterval, f of x4. And so in this picture, our area is approximated by f of x1 delta x, plus f of x2 delta x, plus f of x3 delta x, plus f of x4 delta x. And we can write that in sigma notation as a summation I going from 1 to 4, f of xi delta x. That's our right-hand sum. And in general, the right-hand sum has I going from 1 to n, f of xi delta x. And we could also use other rules to approximate. For example, the midpoint rule uses the function evaluation on the midpoint of each subinterval to get the height of the rectangle. So here on the first subinterval, it's not using x0 or x1, it's using the midpoint here, x0 plus x1 over 2, and taking the function evaluation at that point. That's going to be the height of our rectangle. And similarly for the next interval, so on the ith subinterval, we're taking xi minus 1 plus xi over 2, and we're plugging that into f to get the height of the rectangle. And so our midpoint rule looks like this. Now notice that with any of the rules above, as we increase the number of rectangles, we get a better approximation. So the exact area is going to be the limit as n goes to infinity of the sum I going from 1 to n, f of xi delta x. So we're taking an approximation with n rectangles and then letting n go to infinity. That gives us the exact area. And notice this formula here is using the right-hand sum, but that's really only for the ease of notation because it's I rather than I minus 1. But actually the left-hand sum works exactly the same way, and so does the midpoint rule. So to find the exact area using the limit as n goes to infinity of the summation I going from 1 to n, f of xi delta x, here are the steps. The first thing we're going to want to do is find delta x in terms of n. So delta x is going to be b minus a over n, but remember we don't have a specific value for n, we're going to let n go to infinity. So we get delta x in terms of n, then we get xi in terms of I and n, and xi is given by a plus I delta x, because we're starting at x equals a, and then for the ith subinterval we have to add on I times delta x, the width of each subinterval. And then once we have xi, we plug it into f and find f of xi in terms of I and n. And then we can plug f of xi and delta x in here, set up our summation, and then we're going to simplify and separate our summation into separate sums and use the summation formulas to get everything in terms of n. Then we'll take the limit as n goes to infinity. So let's take a look at an example. F of x is equal to 4 minus x squared on the interval -1 to 1. So first we want to sketch the curve and shade the area under f of x over this interval. Then we want to approximate the area using a left-hand sum with n equals 4. Then we'll do a right-hand sum with n equals 4, the midpoint rule with n equals 4, and then we'll find the exact area by finding the limit here. So first let's sketch the curve, f of x equals 4 minus x squared, on the interval -1 to 1. So 4 minus x squared is a downward-facing parabola shifted up 4 units, so we're here. We know that it has intercepts at -2 and 2, but we're only interested in the area from -1 to 1, so it's that purple shaded area there. Now we know for the approximations we're going to make, we're going to have delta x equal to b minus a over n. So that's going to be 1 minus a -1 over 4, and so that's 1/2. Delta x is equal to 1/2. And so from -1 to 1, we can set up our 4 subintervals here and put markers at -1/2, 0, and 1/2. Now for the left-hand sum, we want to take the function evaluation on the left side of each interval, and that's going to be the height of each rectangle. Notice the width of each rectangle is always the same, that's delta x. And so in this computation I factored out my delta x. And what are the heights of the rectangles here? We have f of -1, we have f of -1/2, we have f of 0, and f of 1/2. Those are the function evaluations that give us the height of our 4 rectangles. And so we plug those into our original function and simplify, and we get an approximation of 29/4. And similarly, we can take a right-hand sum, and on each subinterval we want to take the function evaluation on the right-hand side to be the height of the rectangle over that interval. So over the first subinterval, I'm using the function evaluation at x equals -1/2. F of -1/2 is going to be the height there. On the second subinterval, we're using f of 0, then f of 1/2, and then f of 1. And so those are the heights of our rectangles for the right-hand sum, and so our approximation looks like 1/2, again that's the delta x that we factor out, f of -1/2 plus f of 0 plus f of 1/2 plus f of 1. And here as well we're getting 29/4. And in general the left and right-hand sums will not be the same, but because of the symmetry of the function and of the interval here, they are the same. Let's take a look at the midpoint rule. Now we want to take our function evaluations at the midpoint of each interval. So on the first subinterval, we're taking a function evaluation at -3/4. So f of -3/4 is going to give our height for the first rectangle. On the second subinterval, we have f of -1/4. That's that height. On the third subinterval, f of 1/4. And on the fourth subinterval, f of 3/4. And so our area approximation looks like this. Again, I've factored out delta x here. And so this comes out to be 59/8. Now let's take a look at finding the exact area by taking the limit here. We have the limit as n goes to infinity of the summation I going from 1 to n, f of xi delta x. And let's go back up to the steps we had above to see how to begin. We want to start by finding delta x, then xi, then f of xi, and then we're going to plug them into the limit. So here, delta x is b minus a over n. And now for the exact area, we don't have a specific number of rectangles because n is going to go to infinity. So this is going to be 2 over n. And that's going to go in there for delta x. Now we want to find xi. Xi is always going to be a plus I delta x. So our a value here is -1. This is the beginning of our interval. Our subintervals have width delta x, that's 2 over n. So x1 is going to be -1 plus 2 over n. And then to get x2, we want to add another 2 over n. So that's going to be -1 plus 2 times 2 over n. So in general, xi is going to be -1 plus I times 2 over n. So -1 plus 2i over n. That's how we're going to represent xi here. Now what do we need? We need f of xi. So let's take this expression for xi and plug it into f. So we have f of -1 plus 2i over n, which is 4 minus -1 plus 2i over n quantity squared. Now let's simplify this by multiplying out. So multiplying out, we have a +1. We have -2i over n and another -2i over n, so that's -4i over n. And then we have a +4i square over n square. And now simplifying by distributing through this negative, we have 3 plus 4i over n minus 4i square over n squared. Now let's plug that in for f of xi. And we know that delta x is 2 over n. So that goes here. Now at this point we realize that 2 over n is just a constant in this summation, and it could be pulled outside. But if you don't realize that, that's perfectly okay. You're going to multiply through, like I did here. You're going to have 6 over n plus 8i over n squared minus 8i squared over n to the third inside your summation. Now, in order to use the formulas that we have for summations, we want to separate this into 3 separate sums. So the limit as n goes to infinity stays outside of everything, so we've got big brackets here. And we have the summation as I goes from 1 to n of 6 over n, plus the summation 8i over n squared, minus the summation 8i squared over n to the third. Now, as we mentioned before, the 8 over n squared and the 8 over n to the third here, those are just constant multiples. I is the index of the summation. The 8 over n to the third is just a constant multiple, and that can come outside, just as the 8 over n squared can here. So now our summation looks like this, and this is the form we're looking for because we have our summation rules. We have the sum of a constant, we have the sum of I, and the sum of I squared. So the summation I going from 1 to n of a constant is that constant times n. The sum of I is n times n plus 1 over 2. And the sum of I squared is n times n plus 1 times 2n plus 1 over 6. And so we're here. Now at this point we want to take the limit as n goes to infinity. Well, for the first term, the n's cancel and we just get 6, so that limit is just going to be 6. Notice here we have n squared as the highest power in both the numerator and the denominator. And so we're just going to take the ratio of the coefficients as that limit as n goes to infinity. So in the numerator it's 8n squared, in the denominator it's 2n squared, and so 8 over 2, that gives us a limit of 4. We have the same type of thing happening here. We have n to the third as our highest power in the numerator, also n to the third as the highest power in the denominator. So again, we're looking for the ratio of the coefficients of those terms. In the numerator, be careful, we have 8 times n here, and then times a 2n. So that's going to be a 16n to the third over a 6n to the third, and that's going to give us 8 over 3 as our limit. Now we've taken the limits and we just want to simplify. And so this simplifies to 22 over 3, and this is the exact area under the curve. Now we're going to see in lesson 26 a shortcut way to find these areas by using a definite integral. And so here is our original function, 4 minus x squared, and this is the interval over which we are looking for the area. We want to take an antiderivative, and that's going to be 4x minus x to the third over 3. And then we want to plug in our bounds and subtract. So we plug in a 1, we plug in the negative 1, subtract those values, and we get 22 thirds. So we're going to see in lesson 26 that we don't have to take these long limit computations to find the areas. We'll have a shortcut way to do that. And so I'm just giving you a little preview here so that you can check your work. Now, in some cases, we might not have the function formula for f of x. We might just have a table of data. So for example, speedometer readings of a motorcycle are given at 12-second intervals. And so here are our time values in seconds, and here are our velocity values in feet per second. And we're asked to estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the intervals. Now notice that it says using the velocities at the beginning of the intervals. That's talking about a left-hand sum. And then in part B, they ask us to do the same, but they say take the velocities at the end of the intervals. That's going to be a right-hand sum. And then they want to know if the estimates are upper and lower estimates, and we should explain. So to start, I think it helps to plot the data. So the points here are the data points that we're given. And now these are velocity values at given time values, and they're asking us to estimate the distance traveled. So before we jump into our left and right hand sums, let's talk about why that is the computation we want to make. If we are trying to approximate distance traveled, and we only have data every 12 seconds, one way that we can estimate the distance traveled is to say, okay, let's assume the motorcycle was traveling at 30 feet per second over the entire 12-second interval. If it traveled 30 feet per second for 12 seconds, then multiplying the 30 times the 12 would give us the distance traveled, 360 feet. And we could do that on each interval. So that's why it makes sense that we are taking left and right hand sums here to get a computation for distance traveled. So for our left hand sum, the function evaluations are going to be v of 0, v of 12, v of 24, v of 36, and v of 48. And those are going to be the heights of the rectangles we use here. And our delta x, or delta t in this case, is going to be 12. So we have 30 feet per second times 12 seconds, plus 28 feet per second times 12 seconds, plus 25 feet per second times 12 seconds, etc. And we get 1,548 feet here. And then our right-hand sum, our approximation, also has delta t being 12, so here I've factored that out. And now the function evaluations are coming from the right side of each interval. So we're starting with v of 12, and then v of 24, v of 36, v of 48, and v of 60. So we're using 28, 25, 22, 24, and 27 as our function values. And so that approximation comes to 1,512 feet. And now we're asked here if the approximations we made were upper or lower estimates. And let's take a closer look at the picture here. And we realize that we don't necessarily have upper and lower estimates because the rectangles that we're using with our left-hand sum, for the first 3 intervals, we're overestimating the distance traveled, and then for the next 2 subintervals, we're underestimating the distance traveled. And with the right-hand sum, we have the last 2 subintervals overestimating, and the first 3 subintervals underestimating. And so we didn't find under and over estimates. If f of x is decreasing only, then the left-hand sum would give an overestimate, and the right-hand sum would give an underestimate. If f of x is increasing only, then the left-hand sum would give an underestimate, and the right-hand sum an overestimate. And so here, we're learning how to compute areas under a curve using approximations, then also finding the exact area using a limit. And as I mentioned earlier, by the time we get to lesson 26, we're going to find a shortcut way to compute these exact areas. And this concludes lesson 24, area under a curve.